Hello. Okay. So, Abena, hello, Abena, are you there?
Yes, please.
So, in deep space, the engine of the space shuttle is off. And once it's off, meaning the continuous motion of it is not by it. The space shuttle can, on its own, continue to move within the space freely. They would only put the engine on if they want to change direction or change the speed of the spacecraft. Is that okay? So Newton's first law of motion can be demonstrated in these areas mentioned. On the surface of the earth, it is difficult to demonstrate it because on the surface of the earth, we hardly can have friction-free space, friction-free land, friction-free air, and all that. That is why it can be so difficult to do that on the surface of the earth. And even that, when you are skating on ice, the ice skaters, okay, the ice floor is almost a frictionless surface. So when you are skating on ice and then you just push yourself, you continue to go so long as you have ice all through, confirming the first law of motion. Is that okay? Are we fine?
Yes, please.
Good.
Inertia,
Hello.
please, can you say that? But the first part of Newton's first law of motion is easy to apply. It's only dynamic, as in the fact that an object at rest will only stay at rest when will stay at rest unless an external force is applied.
Yes.
Can you say that it's only dynamic equilibrium that is difficult to see in
On the
real
surface,
life on Earth?
yes, because on Earth, hardly can we have friction-free surface. Even in air, when you throw an object, the object goes and at a point will stop because air resistance, which is also friction in air, is there. Is that okay?
Yes, Mr. Ita.
So in real life, the first part of it, the dynamic one is similarly not so applicable unless other interventions are in place. Are we fine? All right.
Yes, please.
Newton's, let me off the lights. Newton's first law of motion is also said to be the law of inertia. It's also known as, the first law is also known as the law of inertia. The first law is also known as the law of inertia. Now, the question is, what is inertia? Objects by their nature, no matter how small or big it is, by their nature, have that inherent or inbuilt, okay, resistance to change in their position or velocity. Okay, so if an object is at rest, the object by its nature would want to be at rest. When you want to change it from resting to moving, it will oppose it, and that is the inertia of objects. When an object is in motion and you want to stop it, it always want to be in its state of motion. If you want to stop it, then it will resist it. And this ability of object to resist change in their position, okay, nature, or change in their speed is what we call as inertia. Is that okay? What it therefore means is that if a body is stationary and you want it to move, it will require more force to change it from resting to motion. Now, if an object is already in motion and you want it, there's a car in motion. Let it stop before. If a car or a body is also in motion and you want it to come to a stop or come to rest, you require more force, okay, to apply in order to stop it from moving. That is why Newton's first law is also known as the law of inertia. Now, if the body has a smaller mass, inertia is about mass. If the body has a smaller mass, you require a smaller force to change its state, whether resting to move or moving to rest. Now, if the body has a greater mass, then you will need more force, okay, to either act on the body to be in motion, or when it is already moving, to stop it. Imagine, look at this, the Asa ladies, very fat one. The Asa lady is standing there and you want her to move. Okay, you have to push. You don't take Ileana or Mirabel to do that easily. Ileana or Mirabel we need to push, they need to push higher for them to move. Now, when they are also in motion and you want to stop them, you have to apply a greater force in the opposite direction to stop them. Is that okay? So that is why the first law is also known as the law of inertia. Now, overcoming our own inertia or our own mass is applied in daily life. Example, how do we overcome our inertia? Let me draw your attention to an example. If you are in a car, okay, sitting in a car and the car starts moving, and let me put somebody on the spot. Sanam, are you there?
Yes, please.
Sanam, when you are in a car and the car starts moving, what do you usually observe about yourself in sitting in the car?
And so please, if it's like sudden motion, like the car was stopped, then all of a sudden it starts moving fast, then your body will jolt forward a little bit.
Yeah, let's assume the car is stationary, the engine is started, and then the driver starts moving. What do you usually feel with regards to your sitting position? Okay, anybody else can also contribute if you have made that observation. Any observation made? Okay, no observation. You see, when you are in a car and the car suddenly, the driver, okay, starts the engine and begin to move, you usually lean back in your chair. You usually, while the car jolts forward, you will jolt back in your chair. Please, have you made that observation?
Yes, please.
Now, meaning what it implies is that there is a sudden change in position or in velocity, and by your body's own natural inertial frame, masses would always resist change in their velocity. So the car will want to go forward and you want to still be in your position of rest. You overcome your inertia by, you usually feel that the seat on which you sit seems to be pushing you. So there will be a push between you and the seat. Then you react to the new velocity of the car. Please, have you made that observation? When a car suddenly makes a turn, okay, changing direction, same as changing speed, you would always, because the car is in straight line and suddenly turns on changing direction, you will continue to be in a straight line by gluing to the corner of the car. Meanwhile, the car is turning. So the side would have to push you to now follow the direction of the car. That is how we overcome our inertia. So either the side of the car, the chair would have to push you to overcome your inertia. Now, when the car is in motion and suddenly the driver applies the brake to reduce the speed, Akofala, are you there? When the driver suddenly applies brake, now, while the car is moving, the chair on which you sit has helped you to overcome your inertia. Now you are following the velocity of the car. When there's a sudden brake, the car would reduce speed, change speed, velocity. Your body would always want to resist change in velocity. So you will continue to be in motion, straight, being forward, okay, until you hit something, or the seatbelt pulls you back to be in line with the new velocity. That is how we overcome our own inertia, body's inertia. Please, are we fine? Are we okay?
Yes, please.
And because of overcoming our own inertia, that is why the seat belt is so important. When you are in a car, it is a safety precautionary measure to always have your seat belt on. The reason is that if your car is moving forward and there is a sudden hit, okay, and an oncoming car hits your car by this, either in front or by the side. If it hits it in front, once the car hits at you, your velocity will be reduced. The reduction is directly proportional to the car's velocity will be reduced, and is directly proportional to the force which hits your car. You, the passenger in it, would always resist a change in velocity. So whilst the force hits your car to reduce speed by some margin, you would be moving forward by the same margin because you will resist change in your speed. Okay, but you move forward when the car seems to be stopping you by hitting you head on. You will move forward with the force or with the acceleration directly proportional to the force that struck your car. So look at the weight of a car and hitting your car head on. So you also move forward with the same force. So if you don't have your seatbelt on, you hit maybe I've forgotten how to this frontal part of the car where the steer is. Dashboard. The dashboard. You can easily hit the dashboard, or you can throw yourself from your seat through the windscreen. But if you have your seatbelt on, whilst you resist the change in velocity by not going backwards, it will just pull you back and then fix you in your position safely. That is why it's so advisable to always have your seatbelt on. Hello? Are you okay?
Yes.
Okay. All right.
Please, there's a question.
Ask your question.
Seja, please, if the car is in motion,
yes,
and then you as the passenger in the car is resisting the forward movement,
give me
and
a
you
second,
said we
I'm
are
coming.
leaning.
Give me a second, I'm coming.
Yes.
I'm listening.
Please, the car is moving forward.
Yes.
You as the passenger are resisting that forward movement, and then like you lean back.
Mm-hmm.
Does it mean that you lean back with the same resisting force as the force that the car is moving forward with?
Exactly. Exactly. Okay. So you will lean back with the same force which is pushing the car forward. Is that okay?
Are you in equilibrium?
Pardon?
Or this doesn't mean that the passenger is in. Would it be right to say the passenger is in equilibrium?
No, here the thing is that you resist change in motion. Okay, by your inertia, you resist change in motion. But then, if the car is moving forward with this velocity, you would also move backward with the same velocity, because at that time your velocity is according to the velocity of the car. Is that okay?
No, mistake. Yeah, I
Here,
don't understand.
no, here, don't talk about equilibrium. I understand your equilibrium, meaning same velocity of the car and same velocity of you moving forward or backwards. But don't categorize that at equilibrium states.
Yes.
Okay? Is that okay? All right.
Mr. Dia, please why?
No, equilibrium has to do with forces. We are
Mr.
not,
Dia.
equilibrium state has to do with the forces, not the velocity.
Okay.
Here we are, our equilibrium state has to do with the forces in consideration. Then, so that explains the first law. The second law, I said the second law of motion talks about how to measure this external force which would cause a body to be in motion. Okay, in the first situation, when the net force is 0, the body can be stationary or move with that constant velocity. Okay, now the body can only move when there is, so when there is a net force, then body will accelerate. Please take note that in the first law, being it static equilibrium or dynamic equilibrium, acceleration is 0. In the first law, being it static equilibrium or dynamic equilibrium, acceleration is 0. Okay, because in the first one, static equilibrium, the body is stationary, has 0 velocity. In a dynamic equilibrium, the body moves at constant velocity. And once there is constant velocity, then there's no change in velocity. So acceleration is 0. Now, if there's a net force and the body is moving, then we say there will be acceleration. Anita and Co, are you okay? So if there is a net force, body would accelerate. Okay, the acceleration of the body, the acceleration A of the body is directly proportional to the net force acting on the body. Ajo, are you fine here?
Yes, please.
So the acceleration of the body is directly proportional to the net force acting on the body. So the second law of motion is defined as whenever there is, or it states that whenever there is a net force acting on the body accelerates. Okay, and this acceleration is directly proportional to the magnitude of the net force acting on the body. So whenever there is a net force acting on a body, the body accelerates. This acceleration is always directly proportional to the net force acting on the body. So simply, Newton's second law of motion mathematically is stated as A is directly proportional to F net. Okay, now in proportionality, when you introduce an equal to sign, there is a constant of proportionality. So if we introduce an equal to, we have a constant K times F. And the constant of proportionality here is that non-changing mass. So K here is equal to the constant mass of the body. So we say A is equal to mF. Or let's bring the I think here the force F net has to come first. So F net is directly proportional to A rather. Sorry, let's take it from the other way round. Rather, the net force must be directly proportional to the acceleration. So if F net is equal to a direct proportional to this, then K is equal to A. And the constant of proportionality here is the mass. Hence, F is equal to ma. Okay, so this Newton's second law of motion explains how to measure the net force which will cause an acceleration of a body. So second law explains how to measure the net force which causes the acceleration of a body. Please, are we okay here? Are we okay?
Yes, please.
Zanam,
Miss Adia.
ask your question.
Sir, please, for now, I don't have a question.
Akovala, Adwa Yabua, Abna Yabua. Ask your question.
Miss Adia,
Hello.
I just want to be sure. Please, by directly proportional, we don't mean equal magnitude, but we mean
No,
that
no.
increase in the other increases.
What would cause an increase? A decrease will cause a decrease,
Decrease, okay.
but not of the same magnitude. Another way to look at Newton's second law of motion is this. You see, whenever I'm moving, Mr. Abia is running, and suddenly there's a net force acting on me, my speed will change. So if I was running slowly and I'm suddenly pushed, my speed would increase, right? And so net force also causes change in speed or velocity. So it implies that once there is a net force, we'll have change in speed or velocity. So net force or any resultant unbalance or net force causes change in velocity. Adwa, once there is a change in velocity, it means the body does what? Adwa has gone to sleep. Eliana. Hey, once there is a change in velocity, it implies the body does what? Hey, Abna Yabwa.
Yes, Mr. Adrian.
Once there's a change in velocity, it implies the body does what?
Sir, please, I didn't get that part.
Once there's a change in velocity, then it implies the body is. Hey, okay. More roll call. Anita.
Accelerating.
The body accelerates. So from here, from F net is equal to MA. Once there is a net force, the body would accelerate. And this acceleration A is given by change in velocity, okay, over time. Change in velocity is final velocity minus initial velocity divided by the time taken. So Mr. Abia is running, okay. As I run, okay, I have my own speed. It may be initial speed, U. Now suddenly there is a net force which pushes me. Once I'm pushed, my velocity will change. So after the exertion of the force, my final speed is V. Now, the time within which I was having an initial speed U and then now a final speed V, the time is the small t. Okay, so small t is the time within which the change in velocity occurred. All right, so my acceleration A is given by the change in velocity over t, which is certainly delta V on t. Let's substitute this into Newton's second law equation. When we substitute, we have m delta V over t. What is delta V? What is m delta V? What is m delta V? Yes, anybody? What is m times delta V? Oh, time. Eliana. M times delta V.
Momentum.
Momentum. And momentum, this is change in momentum. Change in momentum, P over T. This is change because delta V is actually V minus U. Okay, so when we put them apart, we had MV minus MU, all divided by time. What is MV? MV is final momentum. So this is equal to P final minus P initial, all divided by the time T. So we are saying that P final minus P initial is equal to the change in momentum divided by time. And because of this, we also state Newton's second law of motion as the rate of change of momentum with respect to time is directly proportional to the external force applied. So these are two different ways of stating Newton's second law. Either whenever there is a net force, a body accelerates, and this acceleration is directly proportional to the net force applied to the body, or the rate of change of momentum with respect to time is directly proportional to the external force applied. Are we fine? Are we fine?
Mr. Edia,
Hello.
please can you go over?
Go over what?
From the momentum part.
Hey, Akofana.
Oh, Miss, I'm sorry, I went off a bit. I'm very sorry.
Okay. Maybe it will open door for somebody to. What I'm saying is that whenever there is external force applied to cause the motion of a body, either if it's stationary or if it's moving at a constant speed, its speed will change after the external force. So we realize that the external force is directly proportional to, yes, acceleration. So once there is an external force, the body accelerates. But whenever there is external force, the body's velocity or speed would also change from an initial value to a final value. And so we got acceleration, the net force, and the relationship it has with acceleration to be this. This acceleration, which is due to the net force, is given by this. So A is equal to V minus U on T. When you put this in, you have V minus U all on T. When you expand the numerator, we have mv minus mu all on t. What is mv? mv is momentum, but final momentum pf minus mu is initial momentum pi all over t. Please, momentum is denoted as the letter p. Therefore, this is equal to delta p over t. And in conclusion, we can say F is equal to delta p over t. And this is another way of stating Newton's second law, that the rate of change of momentum with respect to time is directly proportional to the external force applied. Akovala, are you fine?
Yes, Miss Dedia, thank you.
Okay. So from Abna, Yabu, Anita, and the rest of you, are you fine?
Yes, please.
Okay.
Yes, please.
Yes, please.
From here, we can also conclude that F by T is equal to delta P. And what is F times T? F times T is impulse. Impulse. So impulse is equal to the change in momentum. Impulse is equal to the change in momentum. So if you're asked to calculate for impulse and the initial momentum and the final momentum is given, the change is equal to that. And if you are also asked to calculate for change in momentum and the force and the time is given, the product of the force and the time is equal to the change in. So they depend on one another. Is that okay? So that does it for Newton's second law of motion. So the first law establishes the link between force and motion. The second law establishes how to calculate for this net force which will cause motion. And the third law talks about a certain pair of forces and their interaction with each other. Any question? Now, Newton's third law of motion. So it talks about, it's like a conjoint, it's like conjoint twins. Okay, one conjoint twins, but pairs of forces acting on different masses. So all that the third law is saying is that if body A and body B, if body A exerts a force F1 on body B, then body B would also exert the same force F1 on A.